Hello, everyone. Today we are going to discuss a very hot topic, how to build efficient AI agent systems. Over the past year, more and more teams have started to build agent systems based on large language models, LLM. The interesting thing is that the most successful implementations are often not using complex frameworks, but rather adopting simple, composable patterns that let's dive deeper into this field together. First, we need to clarify what an agent is. In the field of AI, agent systems are mainly divided into two categories: workflows and agents. The workflow system orchestrates LLMs and various tools through predefined code path that is like a fixed production line where each step is pre-planned. For example, an automated customer service system handles user inquiries, queries databases, and generates responses according to preset processes. The agent is more flexible and autonomous, capable of dynamically guiding its own processes and tool usage. Imagine an AI assistant that can autonomously program, dynamically deciding which files need to be modified based on the specific task and how to modify them, rather than following fixed steps. When building LLM applications, we should always follow one principle. Seek the simplest solution. In many cases, optimizing a single LLM call is sufficient, and there is no need to build complex agent systems. Why should one be cautious when using multiple LLM calls? Because agent systems typically introduce higher latency and costs. Each additional LLM call means more waiting time and API expenses. This trade-off only makes sense if it significantly improves task performance. There are many frameworks available in the market that can help us implement intelligent agent systems, including the workflow framework LangGraph from LangChain, the AI agent framework Amazon Bedrock provided by Amazon, and graphical interface tools like Rivet and Vellum, which all offer drag-and-drop LLM workflow construction capabilities. These frameworks simplify basic tasks such as invoking LLMs, defining tools, and linking calls, indeed enabling developers to get started faster. However, I suggest developers start by directly using the LLM API because many patterns can be implemented with just a few lines of code. If you eventually decide to use a framework, make sure to deeply understand how the underlying code works, to avoid making incorrect assumptions about how the framework operates. This will not only allow you to better control the system, but also make it easier to debug and optimize when encountering issues. The foundation of the agent system is an enhanced LLM. These enhancements include 1. Retrieval capability, the ability to query and acquire relevant information. 2. Tool usage, the ability to invoke various APIs and services. 3. Memory function, the ability to maintain conversation context. For example, a customer service agent can retrieve product knowledge bases, invoke order system APIs, and remember users' previous questions to provide coherent and targeted service. Next, let's take a look at several common workflow patterns. 1. Prompt chaining. Break down the task into consecutive steps. For example, first generate a document outline. Check if it meets the requirements, and then write the complete document based on the outline. 2. Routing. Distribute tasks to specialized processing workflows based on the input type. For example, categorize customer service inquiries into refund requests, technical support, or general questions, then pass them to the corresponding specialized processing workflows. 3. Parallelization. Run multiple LLM tasks simultaneously. This can involve splitting a large task into independent subtasks for parallel processing, or running the same task multiple times to obtain diverse outputs. 4. Orchestrator workers. A central LLM decomposes tasks and assigns them to other LLMs for execution. Suitable for complex code development tasks, the orchestrator can decide which files need to be modified and then assign them to different workers for processing. 5. Evaluator optimizer. One LLM generates responses, while the other provides evaluation and feedback, forming an optimization loop. For example, in literary translation, the evaluator can point out subtle issues in the translation, helping the optimizer improve. In addition to the above workflow patterns, truly intelligent agents possess higher autonomy, enabling them to independently plan and operate, continuously acquire environmental feedback, handle open-ended problems. For example, a code development agent can understand task requirements, autonomously plan the necessary code modifications, and continuously test and adjust during execution until the task is completed. In practical applications, truly intelligent agent systems excel particularly in two areas. First is customer support. The intelligent agent can engage in natural conversations while accessing customer data, order history, and knowledge bases that IT can also perform actions such as refunds. Success cases show that some companies have started adopting billing models based on resolution rates, I.e., charging only when user issues are successfully resolved, proving the feasibility of this approach. Then comes code development. In the field of software development, agents are particularly effective because code solutions can be validated through automated testing, and agents can iteratively improve based on test results. Moreover, the problem space is well structured, and the quality of the output can be objectively measured. In practice, agents are already capable of autonomously solving real-world problems on GitHub based on pull request descriptions. However, it's important to note that while automated testing can verify functional correctness, human review remains a critical step to ensure the solution meets the overall system requirements. Therefore, when building agent systems, we should follow three core principles. 1. Maintain design simplicity. Do not complicate for the sake of complexity. Only add complexity when it is truly necessary. Point 2. Ensure transparency. Clearly display the planning steps of the agent to help users understand the system's decision-making process. Point 3. Carefully design the agent-computer interface. Just as we value human-computer interaction, HCI, the design of the agent-computer interface, ACI, is equally important. Clear documentation, examples, and boundary definitions are needed to guide the agent in correctly using tools. When building agent systems, the design and implementation of tools are equally crucial. As we previously discussed various workflow patterns, tools are the foundation for agents to interact with the external world. Let's take a look at specific recommendations for tool design. 1. Focus on tool documentation and descriptions. Write clear documentation, including usage examples, edge cases, and formatting requirements. Write it as if you are writing documentation for junior developers. This is directly related to the transparency principle mentioned earlier. 2. Choose the appropriate format. Select a format that is close to the natural format commonly found on the internet. Avoid complex format requirements. For example, use Markdown instead of JSON, requiring escaping to wrap code. This can reduce the error rate of the intelligent agents. 3. Testing and optimization tool usage. Test various inputs in the workbench. Observe potential errors the model might make, and continuously improve. This is crucial for ensuring the reliability of workflows and agent systems. 4. Mistake-proof design. Modify tool parameters to make errors less likely. For example, using absolute paths instead of relative paths in file operations can significantly reduce path errors. This design concept is particularly applicable to the code development scenarios discussed earlier. In conclusion, building a successful agent system is not about creating the most complex system, but about building the system that best suits your needs. Start with simple prompts, optimize them through comprehensive evaluation, and only add multi-step agent systems when simpler solutions are insufficient. This is the core principle we emphasized at the beginning of this article. Thanks for watching. If you found the video helpful, please like and subscribe. See you in the next one.